Today, we're plunging into, well, two worlds that seem almost like opposites: abstract math and really cutting-edge physics.
Hmm.
We're exploring this fascinating, almost paradoxical convergence of topological quantum field theory, let's call it TQFT, and quantum chaos, and how this all somehow touches on cosmic complexity.
It sounds like a lot, but the connections are surprisingly deep.
Exactly. And our mission today, for you listening, is to cut through the jargon. We want to get to the core ideas, zeroing in on how quantum chaos and TQFT, which seems so different, are actually connected.
Right, how they influence each other.
What does one field get from the other? And crucially, what are the absolute essential concepts you need from each side to really see that bridge between them?
And it's important to stress, these aren't just, abstract ideas gathering dust. This is active research. We're drawing on stuff appearing right now on places like the arXiv preprint server. It's really the frontier.
Absolutely. So picture this. We're digging into how something built for robustness, for topological protection, something meant to be stable, can almost counterintuitively show chaotic behavior.
Yeah, order somehow leading to a kind of controlled chaos.
That's the puzzle. That's what we're going to try and unravel today.
Yeah.
So to get started, let's define our terms. First up, topological quantum field theory, TQFT. At its heart, what is it?
Okay, so TQFT, it's a special kind of quantum field theory. The key thing, the really defining feature, is that the physical measurements you can make the observables, they only depend on the topology of spacetime.
Topology. So like the overall shape, connectivity, not the exact lengths or angles.
Precisely. Think about stretching a rubber band. It's still a loop, right? The topology hasn't changed even though the geometry has.
Yeah.
TQFT cares about the loopness, not the specific stretch shape.
Okay, got it.
Edward Witten introduced these back in the 80s. And they're incredibly powerful for understanding systems with what's called topological order. Things like fractional quantum Hall states. Well, maybe exotic particles called anyons.
Anyons,
Oh.
right. Not bosons or fermions, something else entirely.
Exactly. TQFT assigns mathematical objects like Hilbert spaces. Think of those as the space where all possible quantum states live to different shapes, different manifolds, and it computes these things called invariants.
Invariants, like the
Right.
Jones polynomial for knots, something that stays the same even if you wiggle the knot around.
That's a great analogy, yeah. These invariants are robust against continuous changes. So the big takeaway for TQFT is global properties rule. Local details don't matter as much, and states are often very robust against small disturbances. That's the topological protection idea.
Okay, so TQFT, robust, global, protected. Now, let's flip the coin. Quantum chaos. Sounds like the complete opposite. How does that work?
Well, it sort of is the opposite focus. Quantum chaos looks at quantum systems, where the classical version, like if you imagined it as billiard balls instead of quantum waves, would be chaotic.
You mean like the butterfly effect? Tiny changes, huge consequences.
Exactly that. But quantum mechanics is different. It's linear. Energy levels are discrete. These things tend to wash out some of the really obvious signs of classical chaos. So quantum chaos is more subtle.
Subtler how? What are we looking for then?
We look for different signatures, things like how energy levels are statistically spaced apart, or how quantum wave functions might sort of scar along the paths a classical chaotic particle would take.
Interesting.
And maybe most importantly, how quantum information spreads out. We call it operator spreading. Imagine dropping ink in water. The information about where the drop was quickly scrambles throughout the whole glass. Quantum chaos studies that kind of scrambling.
Okay, and this relates to black holes and stuff.
Very much so. That rapid scrambling is crucial for understanding things like how black holes process information, or how quantum systems reach thermal equilibrium, this idea called the eigenstate thermalization hypothesis. It's about how complexity emerges from seemingly simple rules.
Right, so we've got TQFT, all about stability and protection, and quantum chaos, all about sensitivity and scrambling. They really do sound like oil and water. How on earth do they connect? It feels contradictory. How can something be both protected and chaotic?
That's the million-dollar question. And it's where things get really fascinating. Recent research is showing that despite that inherent robustness, TQFTs can actually show chaotic behavior. In certain situations, certain limits.
Whoa, okay. So the protection is an absolute immunity to chaos. Let's
Right.
unpack that. How does that work? How can chaos sneak into a TQFT?
We'll take a TQFT in 2 + 1 dimensions, 2 space, 1 time. The dynamics of those anyons we mentioned.
The weird particles.
Yeah, how they move and interact, especially how their paths braid around each other, which is a topological thing.
Yeah.
The braiding, or even just defects in the topological system, can actually start to mimic chaotic scrambling.
So the topological rules themselves can lead to complex, scrambly behavior?
In a way, yes. It's not just random noise. It resembles the kind of quantum chaos we see in other complex systems. There's research, Wang and collaborators looking at this in things like fractional quantum Hall systems. They use tools like that operator spreading ID.
Like things spreading out?
Right. And another key tool, out-of-time order correlators, OTOCs.
OTOCs. Okay, that sounds technical but important. What do they measure?
They're a really clever way to diagnose chaos in quantum systems. Imagine you could somehow measure how much a tiny change now affects something in the past. It's not quite time travel, but it mathematically probes that sensitivity. OTOCs quantify how quickly information gets scrambled and tangled up,
Ah, okay, so they're like a scrambling meter.
pretty much. And what the research found is that the topological structure of the TQFT doesn't stop the scrambling, but it constrained it, it channels it. This leads to this new idea: topologically protected chaos.
Protected chaos. So the global rules limit how chaotic it can be.
Exactly. The global symmetries put boundaries on the information scrambling. It's not just chaos running wild. It's chaos operating within strict topological rules. It's a controlled, structured kind of chaos.
Wow. Okay, that's a fundamental shift. It's not order versus chaos, but order shaping chaos.
Mhm.
So for you, the listener, trying to connect these dots, what are the absolute must-know concepts from each side?
Right. Boiling it down. From TQFT, you absolutely need topological invariants, that core idea of robustness, properties that survive stretching and bending, the fundamental blueprint.
The unshakable foundation.
Yes. And second, anyonic dynamics. Understanding these unique particles and how their braiding, their interactions, encode the system's deep structure and can generate complexity.
Got it. TQFT invariants and ennions. What about from the chaos side?
From quantum chaos, the key things are, first, information scrambling. That rapid dispersal of quantum information like the ink spreading, it's the process at the heart of quantum chaos.
The mixing process.
And second, out-of-time order correlators, OTOCs. Remember these as the diagnostic tool, the scrambling meter, that lets us actually see and quantify this chaotic mixing in the quantum realm.
Okay. Invariants and ennions from TQFT. Scrambling and OTOCs from quantum chaos. It really feels like TQFT sets the stage, defines the rules of the game, and quantum chaos describes the actual complex dance that happens within those rules.
That's a great way to put it.
Yeah.
And this connection, this interplay, it actually opens doors to even bigger ideas.
Like cosmic complexity, you mentioned black holes earlier.
Exactly. Quantum chaos is deeply tied into black hole physics and holography. That fast scrambling we talked about, it's thought to be what happens to information falling into a black hole. And its speed is related to something called complexity growth.
Complexity growth, like how difficult it is to describe the state.
Sort of, yeah. How complex the quantum state becomes over time. There's this principle called the arXiv correspondence, a kind of mathematical dictionary linking gravity theories with quantum field theories.
And duality, right?
Right. And in that framework, chaotic dynamics in the quantum field theory side translate into gravitational things on the other side, like the growth of wormholes, maybe. Susskind and others have explored how OTOCs, our chaos measure, relate to black hole complexity. It suggests chaos and gravity are deeply linked.
And TQFT fits into this grander picture too, beyond just particles on a chip.
Increasingly, yes. In simplified models of quantum gravity, like in 2+1 dimensions, TQFTs like Chern-Simons theory actually describe space-time itself.
Wow.
And then the complexity of the quantum states and the corresponding field theory can have a topological interpretation. Researchers like Caputa and Magan have shown connections where topological invariants in the TQFT relate directly to complexity measures. So topology seems to constrain the very resources needed to describe quantum gravity states.
So all three, TQFT, quantum chaos, cosmic complexity, they're all converging on information and topology.
Pretty much. It seems they all point to the fundamental roles of information, how it spreads or scrambles, and topology, the underlying robust structure in quantum systems, especially when gravity gets involved. In these holographic models, you see chaotic dynamics, topological structures, and complexity measures all becoming intertwined. It's like different facets of the same underlying reality.
It's a unified picture emerging from seemingly disparate fields.
Yeah, there's work exploring how even topological phases in quantum field theories show chaotic signatures, and how complexity growth can signal topological changes happening in the gravity side of the duality. It really ties TQFT, chaos, and complexity together.
So we've taken quite the deep dive today. We started with TQFT and quantum chaos seeming like polar opposites.
Right, one about stability, the other about scrambling.
And we've ended up seeing this really profound interconnection.
Especially this idea of topologically protected chaos. It really changes how you think about it. Robustness doesn't just prevent chaos, it can actively shape it, structure it.
It definitely paints a much more nuanced picture of the quantum world. The lines between order and chaos, structure and scrambling, they're really blurred.
And potentially very useful lines to blur.
Useful how?
Well, understanding this has real implications, maybe for building more robust quantum computers, leveraging that topological protection even amidst complex dynamics, or for deepening our understanding of black holes, or even the very early universe.
So for you listening, grasping these core ideas, TQFT's robustness, quantum chaos's scrambling, and their surprising connection, it puts you right at the forefront of some incredibly exciting physics. You're getting a glimpse of a universe that's far more subtle than just simple order or simple disorder.
It's a universe where order can give rise to a very specific, constrained kind of chaos.
Which leads to a final thought to maybe mull over. If topology can protect systems while allowing a constrained form of chaos, what new possibilities does that open up? Could topologically protected chaos be harnessed for quantum technologies? Or does it tell us something fundamental about how information itself is woven into the fabric of spacetime? Is chaos maybe not just noise, but a necessary ingredient for the universe's complexity?